Hello, hi. Thanks everyone for coming. Okay, we can, I think we'll try to make this quick so that we can finish by the 12 o'clock coffee, and if we have time for questions, we'll squeeze that in as well. So I'm gonna, hi, my name is Justin Shenk, and can everyone hear me okay?
Yes.
Okay, thank you. So, can everyone see? Not yet. 1 second, please. Okay, great. Okay, super. So yeah, thank you. Welcome. Again, my name is Justin, and I'm going to introduce some experiences, some tips, things that I've learned while building an emotion detection application for a production environment. And so emotion detection, it's certainly relevant for programmers. If you're in this room, you're interested in programming Python. And yeah, I know I'm somewhere on the autism spectrum, so detecting emotions is something you can always build that skill for. But what I want to show you is first the kind of end product. So this is a GIF that is not loading, but you can go to deepemotion.io and check it out. There's source code for graphical user interface where you can drag a video and get from the video, you can split the video into frames and get the facial expressions read from the frames. And what that's useful for, we'll talk about. So first I'll introduce myself, and we'll go into some emotion detection use cases. I'll talk about neural network architecture training, implementing this in a Flask website, and some additional resources. First, quickly, can I see who here has trained a neural network before? Ah, great. Who here has used Flask or Django for some projects? Okay, great, a lot of overlap. So there's some computer vision, some deep learning, and some web in this talk. So hopefully you can get something from it. So about me, I'm a data scientist at Peltarion and an independent contractor. Peltarion is based in Stockholm, Sweden, and there's it's a deep neural network model builder. So basically like a graphical visual coding for deep neural networks. So you can do click and drag layers, define your hyperparameters, and also in the previous talk we heard a lot about if you want to do versioning for your data model, for your data and for your models, it's all done through here. So if you have any questions about that, yeah, hit me up later. My background is neuroscience research, so I was interested in understanding the brain and how does memory work and how does motion and speech work. So I got some experience with that, and as an independent contractor, I was developing demos for Intel. I presented at ICML, NIPS, CVPR, and CBIT the past couple of years. So here was an example of that. It's a computer vision emotion detection game called Party Pie. And the source code for that is also available on GitHub. And you open a camera, webcam, and it asks you to show emotion, you show it, and it ranks the players based on how well they show their emotion. So it's a lot of fun. And the research I did with my master thesis with Peltarion was on how to optimize deep neural network architectures. So I'm still working on papers on that topic. If you're interested, come tomorrow at 11 o'clock. I'll be giving a workshop on that as well. So yeah, so emotion detection, we know it can be used in everything from autism therapy to media content analysis. And we know also that hand labeling images really takes a lot of time. So if you can automate that, it adds a lot of value for a business. And also, there happen to be a lot of really good data sets out there. So if you wanted to jump into a project and build your own, you can do that right now. But I guess kind of the takeaway here is it's a $20 billion industry. So definitely there's a lot of incentive to understand this system. So yeah, what kind of data set I was using here it's called FER 2013. It's a public data set from a Kaggle competition, ICML challenge 2013. The images are 48 by 48 grayscale. There's 36,000 images. They were scraped from Google Images, so you could go and reproduce this right now. In fact, I'm trying to create an open data set, one with an open license, like a public license for this kind of work. And the labels, there's 7 different labels: angry, disgust, fear, happy, sad, surprise, neutral. Humans do only 65% accuracy on this. Machine, the best one that the machine can do is 71%. So yeah, barely beating the human observation, but yeah, we can talk about that too. Briefly, what a convolutional neural network is it is the feature kernel in gray being convolved or just moved over the image, which is the blue, so the pixel values. And you do matrix multiplication and you get out the feature map. Okay, so if your kernel has different numbers, you get different outputs here in your feature map, and that's how you can magically find patterns in images with the convolutional neural network. So one of the challenges when building a deep neural network is how do you know what's the right size of your layers? So you know that you need something convolutional, right? It's images, but how do you know how, if you have a dense layer, should it be 10 or 100 or 1,000 units long? That's particularly the point I'll talk about tomorrow at the workshop. And but basically, the most useful thing you can do is use prior work. There's a lot of examples out there, a lot of great tutorials. If you jump in there and try to implement your own from someone else's work, you're starting pretty far ahead. And use some heuristics. You don't necessarily have to reinvent the wheel when you are trying to solve an architecture problem. So in the end, the deep neural network looks like this. I mean, you have 2 familiar things for sure. It's the input and the target, predicting the target. And to get there, there's several convolutional layers. And the accuracy we got on this was about 71% as well. So it was as good as the best public ones. Oh, we have a question already? Yes?
Can you switch off the lights there?
This light, yes. We in the previous session we learned that this is actually a window. So I'm afraid we can't. But let's be thankful for sun, maybe. Yeah, the slides are shared. If they're not in the chat right now, I'll send them afterwards in the Slack channel. Yeah. And the one thing, when I started training my first model on the Peltarian platform, I was, expecting it to get maybe 60% for the first try. And I got 90%, and I thought, oh my gosh, this is great. I've solved this problem. Somehow magically picked the right hyperparameters, and everything was perfect. And then I realized, oh my goodness, my loss function was binary cross entropy, which means that the model was saying, okay, what is your first class? Is it anger or not anger? So it looked at every image and tried to see, is every image angry or not angry? And guess what? It predicted, if it just assumed everything is not angry, it did very well. So that was a good lesson. Okay, so then I fixed the loss function. Categorical cross entropy. We've got multiple categories, right? Angry, happy, sad, neutral. The first thing then that started happening was, okay, well my loss is here on the y-axis. My training loss is going down, beautiful, but my validation loss is way too high. So this is a common issue when you're training models. If you get overfitting, what's one layer that you can add that helps it? Dropout, yeah, exactly. So you add dropout. Dropout is one of the, makes sure that the model doesn't overfit from that specific layer. It turns off half of the outputs from a layer, and then it improves. So I was able to then squeeze that difference down. Also with the confusion matrix, so a confusion matrix showing, okay, here's what the actual labels are, and here's what I predicted. there was a nice diagonal, but there's some classes that were really low, and that could be improved by just simply doing more class balancing. So, for example, the discussed category had very few data instances, so the model doesn't really have to pay too much attention to that category. That could be improved, of course, by simply doubling the amount of data there, or adding some more image augmentation to balance out the classes. And let's talk about, so the challenge here, it's video data. And video data, you want to be able to show that, you want to be able to take a video and split the video into frames. And then from each frame, you want to be able to do the facial expression recognition on that frame. One really common tool for computer vision is OpenCV. So in the back end, you have OpenCV that just takes that video in, has a for loop, it goes through each frame, and then from each frame, it sends that frame to the next step. Okay, so we have individual frames from the video. How do we detect the faces in the frame? Again, OpenCV comes in really handy here because it has a Har cascade classifier out of the box. The Har cascade classifier just looks for the right combination of black and white contrast over the frame, kind of like the convolutional layer that you saw before. And it's really fast, but it doesn't really work with if there's lighting variances or if the person's looking away, for example. So you can also use NTCNN, and I did some tests on that. It's slower, but it's much more precise. So depending on what your use case is, if you need the speed, you have to make the choice of which dependency to use here. And then, of course, we want to serve the response via a Flask endpoint. So I'll talk about that in a bit. One specific thing that is helpful is do a little bit of benchmarking and find out if your image, your input data could be reduced. If you don't need to send the whole 2,000 by 3,000 pixel image, you can do some reduction either on the client side, or in this case, because it was video, I just had a limitation on how large the video file could be before I uploaded it. And then I found out, for example, that I could see how much the prediction, so if the image was correctly supposed to be happy, how much that would decrease by changing the input image size. So that's useful to find out what are your constraints when you're working in a production environment. And the trade-off can be visualized here. So I wanted the high frames per second so I could process lots of video fast, but I also wanted to keep my accuracy. So it turns out that actually changing the image pixels too much wasn't going to help to keep the high accuracy. And also, there's a great blog by Adrian Rosebrock on how to do Flask and Keras APIs. So while Peltarion provides a deployment for you and REST API for deployment, version control, all that, if you're doing this with Keras, here's how you do it. In your post response, you definitely don't want to instantiate your whole model within each response, because that would load up all of your weights. Beginner's mistakes. If you want your model to be available, one thing you can do is move it outside of the response function, the request function, or you can put it in to do multiprocessing, which is good. If you've worked with Keras and deep neural networks, you'll find that Flask is single-threaded, so you have to get these issues with, the model is not within the thread. So it's useful to use a multiprocessing module here and then map the function to that process. Or you can also use TF serving, which is really great. TF serving, basically you have your own REST API running in parallel. So that's actually what I use, and you can try it out too. If you go to Docker pool Justin Shenk /motion serving, you'll get the Docker instance with the TensorFlow serving for this expression recognition. And how to do that, if you have your Docker compose file, you simply have one line to give the name for the Docker component, and the image, it'll pull that image, and which ports do you need to expose. And then it sends then you send your image on your Flask app to this to this address, localhost / and then that works pretty well. Also, since I was reusing a lot of components, I packaged it as a PyPI package, FER, so you can go pip install and play with it. And it works like this. You just open an image, so with OpenCV, for example, and then to do detect emotions with that image. And you get output the bounding box and the expressions. So fun for if you're doing robotics or some kind of like Raspberry Pi projects. Detect when your partner's happy. That's always a good thing to do. Additional things that could be done, since we're running low on time, I'll just briefly mention you can use a Redis server to accumulate all of the requests if you're getting a lot of images in. So that way you get batching, and you send that batch over to your TensorFlow server. Again, like these deep neural networks, you can have you can do inference on many images at once. And also Kubernetes or Kubeflow are super useful for doing scalable distributed inference. So say you want to scale up your nodes because you have a large load and you want to be able to do that automatically. Yeah, Kubernetes will help you with that for sure. All right, so that was briefly it. I can say I can point to real quickly the GIF of the site as we. Okay, maybe not. Just go check out deepemotion.io if you want to see what it looks like, and we'll see if there's any questions. Thank you.